Normally, movement primitive generates nominal plan to be executed by the robot. When the robot executes the nominal plan in the nominal environment, the sensors will read the so-called expected sensor traces. When the robot executes the plan in a changed environment, the experienced sensor traces will deviate from the expected sensor traces. This deviation can be used to drive adaptation of the plan such that the robot can still accomplish the task successfully despite the environmental changes. For mapping the sensor trace deviation delta S to the plan correction C, a feedback model H is required. In this work, we would like to acquire the feedback model by learning from human demonstration. Our main contribution is the definition of phase-modulated neural network, which is a neural network with the nodes in the final hidden layer being modulated by radial basis functions centered on the phase variable p. Because of this modulation, this learning representation can capture the dependency of the adaptation on the movement phase. Moreover, because of the multiplication with phase velocity u, the adaptation term c is guaranteed to converge to zero, which ensures the convergence of the adapted plan. We evaluate our framework on a learning tactile feedback testbed. In this testbed, the goal is to learn feedback models for orientation plan adaptation based on tactile sensory information during the execution of a scraping task. Here, the environmental changes are in the form of scraping tilt board orientation changes. Our framework begins with the recording of nominal behavior demonstration performed on nominal environmental setting. The nominal setting corresponds to the flat orientation of the tilt board. This is followed by the demonstration of adapted or corrected behavior on a changed environment. A changed or non-nominal environmental setting corresponds to a particular tilt orientation of the board. After training the feedback model, we test the model for providing online correction and compare the resulting corrected behavior versus a non-corrected one. We test the model on two different environmental settings. The first one is 5-degree environmental setting, and the second one is 10-degree environmental setting.